thank you for the introduction. I'm going to be speaking about affine invariant orders on the space of positive definite matrices. So as you all know, a partial order is a relation that is reflexive, antisymmetric, and transitive. And partial orders play an important role in several areas of mathematics, including the theory of monotone dynamical systems and operators, as well as the axiomatic theory of means. And in this talk, we're going to focus on the space S plus n of positive definite matrices of a fixed dimension n. So the standard way of ordering elements of S plus n is by the loaner order, whereby we say that A is greater than or equal to B if and only if A minus B is positive semi-definite as a matrix. Now, the loaner order has several properties that follow from the definition. The standard one that's sort of immediate from the definition is translation invariance, which is just based on the fact that the definition is based on translation. Another important property that's satisfied is the affine invariance, which, although not immediate, can be shown in a few lines, and it's actually quite an important property for a lot of applications. So another important aspect of this order is the spectral characterization, whereby A would be greater than or equal to B if and only if the eigenvalues of A minus B are non-negative. So the loaner order is used throughout matrix analysis as a natural order on S plus n. It's sort of taken for granted as something that's given. And it plays a foundational role in many areas. One important area is the theory of matrix monotone functions, whereby we're interested in mappings or functions f from S plus n to S plus n. And we say that such a map is monotone if it preserves the order or causal structure as given by the loaner order. So if A is greater than or equal to B, then f of A being greater than or equal to f of B would mean that f is monotone. And a very important theorem in this context is the Loaner-Heinz theorem, which says that essentially the function of raising a matrix to power r is monotone precisely if r is between 0 and 1, given that n is greater than or equal to 2. So for example, squaring a matrix is not monotone, but taking the square root is. And another area where, again, the loaner order is sort of built into the foundation is the theory of matrix means. So this is important when we have matrix valued data and we want to perform analysis, statistical analysis on such sets. A very important basic tool in statistics, of course, is defining a mean. And this axiomatic approach takes the essentially builds matrix analogs for the basic properties enjoyed by means of positive real scalars. So for example, you have the symmetry condition. The second condition says that if essentially the mean of two matrices should fall in between the two, and the rest are sort of monotonicity and so on in the argument. And again, you see that a notion of order is implicit in these axioms. So axiom 2 and axiom 4 are based on an idea of order being present, and that's always taken to be the loaner order. A very important mean that satisfies all of these axioms is the matrix geometric mean, which finds applications in all sorts of areas. And it's sort of given there in the middle of the slide. And it has a very interesting extremal characterization, whereby it's essentially the geometric mean of sigma 1, sigma 2 is essentially the maximum x, where x is a symmetric matrix that satisfies a given inequality. And again, we see that there's a direct role connection between the loaner order and the geometric mean. And there's a geometric interpretation of this mean also, and it corresponds to the geodesic midpoint of the Riemannian geometry induced by the standard affine invariant metric. So in this context, it's very natural to ask, are there other ways of defining orders on the set S plus n? And if the answer to that is yes, then that means it would have implications for all of these other concepts that are built upon this foundation of the order. Okay, so to answer this, the first observation that we are going to use is that there's a sort of conic geometry associated to S plus n. So specifically, we see that the set of positive semi-definite matrices satisfies all of the properties of a closed convex cone, and the interior of this cone is the set S plus n. So one case where we can get a very nice concrete visualization of this is the case n is 2, where we can, through this bijection, we can set up an identification between matrices in S plus 2 and points within the interior of this cone in XYZ space. And another important observation is that orders on continuous spaces are induced by cone fields. So there's a very nice intimate relation between cone fields and orders in continuous spaces, and indeed a cone field induces a conal order, whereby we say that x is less than or equal to y if we can find a curve connecting x to y which runs through the interior of all the cones along the path. And we see that a lot of the standard orders that we use are actually have a conal interpretation. So for instance, the standard vector order in Rn is precisely the conal order induced by the constant cone field generated by the positive quadrant. And we see also that the loner order has a similar conal interpretation, whereby we can note that tangent space on S plus n at every point is the set of symmetric matrices. And if at that point we take the cone of S plus n in that space to be the cone at that point, then the cone field corresponding to this picture induces a conal order precisely matching this loner order. Okay, so our approach now is to use the homogeneous geometry of S plus n, which is another very important aspect of S plus n, sort of moving away from the translational geometry and using that as a guiding principle to generate orders. So just as a recap, a homogeneous space is characterized by the existence of a transitive action by a group of transformations that act on the space. So if any give 2 points on the space, we can find a group of transformations, an element of a group of transformations that maps one to the other. And an important point here is that this transformation is not unique. There's a whole family of transformations that take one point to another. Okay, and S plus n in this picture can be seen to have the structure of a homogeneous space with a transitive GLN action given by these congruence transformations. And specifically, we see that if sigma 1, sigma 2 are two positive definite matrices, tau A, this congruence transformation with A being the square root of sigma 2 times the inverse of the square root of sigma 1, gives you the map that takes sigma 1 to sigma 2. And again, this isn't unique, and the non-uniqueness is captured by the isotropy group at the identity, which here we can see to be precisely the group of rotation matrices ON. So we see that naturally this quotient manifold structure arises through this consideration. Okay, and so our aim now is to use this homogeneous geometry and construct cone fields that are invariant with respect to it. So the idea of invariant cone fields is that you take some cone at one point, at some base point, say, and then you want to use the geometry of the space to generate a whole cone field based on that one cone. And for this to be possible, you need one consistency condition, which is the ADH invariance of the cone at the base point. So the cone at the base point needs to have some symmetry, and once that symmetry is built in, then you can use the geometry to get a well-defined cone field. And you can sort of see if this symmetry fails, the non-uniqueness of the transformations that take you from one point to another mean that you get different cones at different points if you don't have the symmetry built in. And for many spaces, this isn't possible to build an ADH invariant cone at the base point, but for S plus n, it is possible. And so the basic procedure for constructing these is a two-step process. The first one is to define a cone that's ADON invariant at the identity, at the base point, which is the condition given there. And then once you find a cone that satisfies that, you can then use the geometry of the space to generate the cone field over the whole space. And this condition 1, if you look at it, you see that it's satisfied precisely if the cone has a spectral characterization, meaning that if you are given a vector x in a tangent space, you can in the tangent space at the base point, you can see if x is in the cone precisely by using information strictly to do with the spectrum of X. And so this is just the basic structure that we have. We have this transitive action and the tangent space structure, and the differentials of the transitive action that move you from one tangent space to another. And so we have a very nice family of ADON invariant cones, quadratic cones, given there. So the square of the trace of x minus mu, the trace of x squared being non-negative. Mu is a parameter here, and it parameterizes essentially the opening angle of a certain quadratic cone at the identity. So if mu is 0, we get a half space, and if mu is n, we get a single ray. And as mu increases from 0 to n, we get cones that have sharper and sharper angles at the apex. And so this is actually the spectral characterization of the same cone written below, sort of explicitly showing that it satisfies the ADON invariance condition. And then once we have that, it's just, we can sort of automatically use the geometry to construct a cone field. And if we go through the calculations of all this and try to get a visualization of what's happening in n is 2, we get this picture. So that so if mu is greater than 1, we have the sharper cones, and we see that we have a rotational effect away from the central axis as we move around. And for mu is less than 1, we have wider cones, and we have rotational effects in the opposite direction. And in the special case of mu is 1, we get no rotational effect, and the cone field that's generated against this backdrop of the manifold of S, the manifold S plus n, is essentially coinciding with the translational invariant case. And for comparison, I've included the corresponding translational invariant cone field on the bottom. And so you see that generally you get very different causal structures. And it also shows that in the case mu is 1, which is the loner order in this case, you get a very special situation where the translational invariance and affine invariance sort of intersect. And so it has a sort of somewhat special status there. So each of those orders give rise to different, each of those cone fields give rise to different orders, and generally they would have different properties and so on. And so it's interesting to now revisit monotonicity theory with these new orders. So again, a map would be monotone using the same definition, but we change the order to any of these orders. And so as an analytic tool for studying monotonicity, given that we have a sort of infinitesimal, a local characterization of order through cone fields, it's natural to look for a differential or local characterization of monotonicity, and that's precisely given by this idea of differential positivity, which essentially says that the differential of the map, or the push forward of the map, preserves the cone field structure. So if you start with the cone at one point and use the differential of the map to move to the target point or the image point, the cone is being mapped into the interior of the cone at the target. So it's sort of, the cone is being preserved, as it were. And so for a general map F, we're looking at the differential, and the monotonicity condition, which boils down to differential positivity here, essentially boils down to looking at checking just one implication. That if you start with the inside a cone at one point and push forward with the differential, you're in the cone at the target point. And so this translates into checking that a pair of inequalities imply another pair of inequalities. And I've spared you all the details of this, but if you sort of use this machinery and revisit the Lohner-Heinz theorem, we arrived at this generalization of it, which we can establish that for any of the affine invariant orders, parameterized by mu, and any r between 0 and 1, this mapping of raising a matrix to a power r is monotone on S plus n. And this does not hold for the translation invariant cone fields in general. So it's a very special thing about affine invariance. And another theorem that can be established in this context is something on the geometric mean, whereby we can show that the geometric mean defines a matrix mean according to the axioms for any of the affine invariant orders that are used. And again, this is something that does not hold for the translational invariant orders in general. So a basic observation that we can make here is that we see that the monotonicity of the matrix power function and also the geometric mean are both deeply connected to the affine invariant geometry of S plus n, and not its translational invariant. So even though the lower order is defined using the translational geometry, the reason it satisfies all these nice results is because it happens to be affine invariant, sort of by accident almost. Another observation that you can get through this geometric interpretation that I think is quite nice is there might be a bit of a mystery why the square, on a real line, the squaring and the square root function are both monotone. So why would a matrix have this sort of difference between the two cases? And if you take this cone picture in mind and differential positivity, it becomes almost trivial, because if the square root mapping is monotone, a cone is being contracted or preserved. And so since the squaring map would be the inverse of it, well, it would have to expand the same order structure. So you can't have both being monotone with respect to the same causal structure. Okay, so just to summarize, the choice of order is a key part of studying a variety of problems that is often taken for granted. And using invariant cone fields, and one can use one is provided with the geometric approach to constructing natural orders that connect the geometry of the state space to the search for orders, and coupling this with differential positivity gives a powerful and insightful approach to studying monotonicity. And for future work, well, new notions of orders mean new notions of convexity. Perhaps that could be quite powerful. And of course, one could further explore the applications of these to checking for convergence of algorithms and convergence analysis of algorithms, dynamical systems, and so on and so forth. Okay, thank you very much.
Questions?
Yes?
Yeah,
A long one.
thank you.
Thank you very much for the talk. It was really good. I just wanted to ask if there's, as you increase the dimensions n, is there anything happening? I think in the symmetric matrices, the real simple ones that we know from regular calculus, I think you have to check for smaller dimensions ever to see if a matrix is positive semi-definite or something like that. Is there something like that going on in your orders too, where you increase orders, you increase dimensions? Does that imply some encompassing, or that the smaller dimensions are also positive semi-definite as you increase your order?
Sorry, I'm not entirely sure I got the question. Could you?
You're working on S2, for instance, in your examples. As you move to higher orders, S3, S4, can you say something about the smaller orders, or the other way around?
The smaller orders, well, the orders are defined for any given n, and I don't see how the smaller orders would come into the bigger picture. I think I probably misunderstood the question on some level. Yeah, sure, but if you could clarify that later, that would be. But yeah, the orders are defined for any n, and all the main equations are the same. And all of the results we established, we didn't have any difficulty. N is 2 or 1,000, it's all the same analysis as far as that is concerned. And for any n, you get 2 inequalities that characterize the cone, because they're quadratic, and so you have one equation essentially, one main equation.
Any other question?
The inverse function reverses the Loeffner order. What your generalized order?
Yes, this does exactly that for all of them. They all do the same. I think the gentleman there.
Sorry.
You mentioned for the application. One of the applications that I see is when you want to approximate a matrix by another sampler matrix. Do you know about any application of this work on matrix approximation?
Well, no, we haven't really. I mean, it's sort of new. We just sort of got this result and thought it could be applicable to a lot of things, but we haven't really gone into exploring it in much detail. But yeah, that seems like an interesting thing to look at. I mean, generally, the main motivation was monotonicity is a very powerful, gives a lot of powerful constraints, and sometimes you look at a map and you say, oh, I wish this was monotone, and you check with the lower order and you say it isn't, but then you think, well, maybe it is in a disguised form and perhaps I'm not looking at the right order. I mean, this is quite common in Rn, say, where something that isn't monotone with respect to the positive orthant might be monotone with respect to some other tone.
All right. Thanks again.